Now that we have defined the concept of torque and we have learned how to calculate it, let's investigate what does the torque create. Up to now, we have been a little bit sloppy and we use the word rotation. So we've seen that whenever we have a force being applied about a particular point and it's not being applied directly at this point, therefore there is r vector, which is non-zero, then this force creates a torque, which in turn creates a rotation, either clockwise or counterclockwise in two dimensions. Let's be a little bit more specific and see exactly what does torque produces. In order for us to do so, we need to go back to Newton. And before I start deriving the torque, let's refresh the interpretation of Newton's second law. And we'll use the functional form that assume that m is invariant. Remember, this law is telling us that every time you apply an external force m to a particular system, a sum of the force or a bunch of forces F to a particular system of mass m, this system will be accelerated by a. And remember that m acts like inertia, which is that for a given force, the bigger the inertia or the bigger the mass, the smaller the linear acceleration. So m, which is the inertia, when you do translation, acts like a resistance to acceleration, and in this particular case, to linear acceleration. We have also seen that the direction of F and A, which is the linear acceleration, are always the same because m is just a scalar. So with this in mind, all we have to do now to investigate what really causes a torque is to take the cross product of Newton's second law with our position vector r. The left hand side will become obviously r cross F, which is what we had defined as a torque. So that's easy. Up, left hand side is done. But let's investigate the right hand side. Now we have r cross the product of a scalar with a vector. In this particular case, we know that we can extract the scalar out because it commutes. So this becomes m times r cross a. So far so good. Now what I would like to do is replace my linear acceleration, a, by my angular acceleration. So I need to remember the relationship between the two. And I remember that a is equal to alpha cross r by definition. And remember that the order is important. So let's plug this into my little a. And let's see what happens. I have m times r cross, and let's make sure that we keep the order, because remember for cross product it's important. Bang! So now you have a double cross product. How are we gonna handle this? Well, graphically, if we try to imagine what's going on, we call circular motion. We have r here. We're dealing here with the linear acceleration, which is tangential in this particular case. So let's pick the case of a tangential. We know that the alpha is perpendicular to both, in or outside the page. So alpha cross r will give us a vector which is perpendicular to both. And in this particular case, it will be in the same page as r. Then we're going to take the cross product of this vector with r again, which will give us a vector again, which is parallel to alpha. So that's where we're getting at. Now, technically, what are we going to do with this? Well, we are in good luck because there is an identity for this, which says the following. A cross B cross C is equal to B times A dot C minus C times A dot B. So who's who? Obviously, A is the same as our first R. B is our alpha, and C is our R again. So let's fill that in. B is alpha, so we have alpha times A dot C, R dot R, minus C, which is R, times A dot B, R dot alpha. Now again, remember that when we related A with alpha, we were talking about the tangential acceleration. So A tangential was perpendicular to R, which was also, and R was also perpendicular to alpha, which is out of the page. So R and alpha are perpendicular to each other. Therefore, bang, this is 0. So we end up with alpha, and R dot R is nothing else than a scalar R squared. So really, all this is R squared alpha. So if we put everything together, we end up with sum of the torque is equal to m R squared alpha. Now let's recall Newton's second law. F is equal to ma. So the same way as when we discussed the fact that if you apply a particular force to an object of inertia m, this object will be accelerated. Now we can say that if a torque is applied to a particular system of mass m, this system will be accelerated in the angular direction. So instead of using translation case, we are not dealing with the rotation case. So every time you have a force about a particular point, that means r is not 0, you have a torque. And whenever you have a torque, you have now an angular acceleration. So the same way as a force creates a linear acceleration, a torque will create an angular acceleration. Yeah. Okay, now let's look at those two terms. M was referred as the concept of inertia. Well, the same way, mr squared will also be referred as the concept of inertia, but it will be called moment of inertia. And it will be defined as I. So I is defined as mr squared. To be more general and specific, moment of inertia is defined like this. So what does that mean? Well, I now, or the moment of inertia, does not depend only on the mass, like regular inertia, but it also depends on the mass distribution. And when I say distribution, I mean the distribution of the mass with respect to the axis of rotation. Because now remember, we're dealing with rotation. So, example, if you have a rigid body like this, any shape, and this object is rotating about this axis. Let's say I'm applying a force like this, F, which will tend the whole system to rotate about this axis of rotation. If I apply a particular force, I will create a particular torque. This object has a particular mass, therefore this object will undergo an angular acceleration in the direction of my axis of rotation. Now, if I had the same object of the same mass, but now the mass is being distributed very differently, much further away from the axis of rotation, and I apply the same force, what's going to happen? This force will also create a torque, which will also create an angular acceleration. But since the mass is distributed, so all those little pieces of matter, much further away with respect to the angular axis of rotation, all those little r's, ri, r1, r2, r3, are much bigger. Therefore, I is much bigger. And if I is much bigger, then alpha is much smaller. So the same way as m was a factor that would be uh, preventing linear acceleration or goes against linear acceleration, moment of inertia also has the same effect. So another example would be ice skaters. If the ice skater has long arms spread out, then the mass distribution is further away from the axis of rotation. And if you push with a particular force perpendicular to the page, this ice skater will be accelerated in the angular direction. Now, if you have an ice skater with, say, small arms, yeah, well, and you apply the same force, since the moment of inertia in the second ice skater B is smaller than the ice skater A because the distribution of the mass is much closer to the axis of rotation, or the r is much smaller, then obviously the angular acceleration of this particular person would be much bigger. So when we talk about moment of inertia, we always need to remember that it depends on two things. First, not only the mass, but also the position or the distance of the mass with respect to the axis of rotation. Another example is if you have a bar rotating about this axis, then let's say you consider the center of gravity of this part of the bar, which is halfway. This center of gravity is distributed at a distance r. Similarly, the center of gravity of this part of the bar is here, so this is another r. If you do the same thing now, but you rotate this bar about a center of rotation right here, then the center of mass is right here, which is located at a distance which is now 2r. So obviously 2r is much bigger than just r, therefore the moment of inertia of case A will be much bigger than the moment of inertia of case B. And therefore if you try to apply a particular force perpendicular to the page to try to rotate either the bar around this axis or around this axis, the acceleration of this one, B, the angular acceleration, will be much higher than in this case because here you have a small I and here you have a big I. So I, by definition, and for a point particle, will be mr squared. So for a point particle, I is mr squared. If you're dealing, say, with a disk rotating about an axis located at its center, such as this, then I will be 1/2 mr squared. If you now have a sphere, solid sphere, rotating about an axis at its center, then I is equal to 2/5 mr squared. Actually, 2/5, yeah, but I forgot if it's a hollow sphere or solid sphere. So look it up. There's always a table that you can find in all physics books. They will give you the moment of inertia about various subjects, depending where the axis of rotation is. So you will, what I'm trying to get at is you will notice that the functional form is always the same, always mr squared. The only thing that changes is the numbers that are multiplying mr squared, which will depend on the shape and which will depend also on the position of the axis of rotation. So final thing, let's look at the units of I. I is defined as mr squared. The units of m is kilogram. The units of r is meters, which are being squared. Therefore, the units of I is kilogram meter squared.